A short circuit in an industrial substation releases enough thermal energy to vaporize metal and shower the floor in sparks. In systems like HVDC grids or electric vehicle fast chargers, surviving these high current transients depends entirely on how quickly that heat can be moved away from the components. Engineers often face a difficult choice when selecting components, as the options frequently appear identical on a standardized specification sheet. When a 36,000 amp surge hits, the internal heat follows one of two paths. Either the energy dissipates and the system survives, or the heat becomes trapped, triggering a runaway failure. To understand the difference, we monitored two distinct test subjects: the common insulated module diode and the heavy-duty Press-Pack diode. Both of these components use the exact same internal silicon chip and carry the exact same nominal power ratings. However, in lab testing, they behaved very differently. The insulated module failed at 30,000 amps, while the Press-Pack survived the full 36,000 amp surge. This suggests that the survival limit of a component is determined by something other than the silicon itself, specifically the physical architecture surrounding the chip. The most significant variable in survival is the physical pathway available for heat to leave the device. This schematic of an insulated module shows a single-sided cooling structure. Heat generated during a surge must travel downward to the heatsink. It hits a bottleneck at the aluminum nitride isolation layer, creating a restricted pathway that traps thermal energy near the silicon. This modular design is widely used because it simplifies installation and provides reliable electrical isolation between the circuit and the cooling system. The Press-Pack diode uses a different internal structure based on pressure contact technology, or PCT. By clamping the silicon directly between two metal plates, the Press-Pack allows heat to move in two directions. As the arrows show, energy escapes through both the top and the bottom heatsinks simultaneously. Under a 30 kiloamp surge, the Press-Pack manages to keep its junction temperature at 427 degrees Celsius. In the module, that same energy is trapped, causing the temperature to hit 632 degrees. Double-sided cooling keeps the internal temperatures within a safer range, though it requires a more complex mechanical clamping system to keep the plates in contact. Beyond temperature limits, we must also consider the physical result of a total failure. Inside the insulated module, the extreme heat eventually causes the chip's metallization to evaporate. Because the module is encased in resin, those evaporating gases expand rapidly within the shell. If the pressure exceeds the strength of the casing, it can cause a sudden, forceful rupture. The Press-Pack avoids this by omitting resin encapsulation entirely, relying instead on high-pressure mechanical contact. If the Press-Pack fails, it typically collapses into a contained short circuit. It remains a solid path for current rather than creating an open arc. While both devices are destroyed at their absolute limits, the Press-Pack tends to fail in a way that protects the rest of the system, whereas the module can become a hazard to nearby equipment. This rapid failure is driven by thermal runaway, a feedback loop where a component's physical properties accelerate its own destruction. The loop begins as heat rises, which increases the dynamic resistance of the silicon. Higher resistance causes a larger voltage drop, which in turn generates even more heat. This graph shows the voltage drop for both devices during a 30,000 amp surge. The module's orange line climbs significantly higher than the Press-Pack's red line. At the peak, the Press-Pack shows a 14.6 volt drop, while the module hits 21 volts. That extra voltage drop means the module is dissipating much more total power internally than the Press-Pack. This extra power dissipation feeds the heat back into the chip, continuing the cycle until the silicon eventually cracks under the stress. The single-sided architecture of the module forces it into this self-reinforcing failure cycle much earlier than the dual-sided Press-Pack. Choosing between these two technologies requires balancing installation complexity against the needed level of survivability. We place the insulated module in the lower left quadrant. It is efficient to install, but has a lower ceiling for surge reliability. This makes the module a practical choice for standard industrial converters and basic EV systems, where cost and space are primary concerns. To use modules safely, engineers must pair them with active protection circuits capable of cutting power before a surge reaches the 25 kiloamp threshold. The Press-Pack diode sits in the upper right quadrant, offering maximum surge survivability at a higher cost of implementation. It is the standard for mission-critical systems like HVDC transmission lines and heavy traction equipment, where the system must survive extreme fault conditions. Designers selecting the Press-Pack must budget for the physical footprint and the mechanical hardware required for high-pressure clamping. Ultimately, a component's performance in a fault depends on more than a simple silicon rating. Reliability is achieved by matching the internal thermal architecture to the actual surge risks of the environment.